Hello. My name is KATHRYN Chain. I am from the University of Nebraska at Omaha, and this is my research report for the Texas A&M REU on July 24th, 2024. My project is titled Prototyping Inhomogeneous Swelling Responses in Polymer Gel Systems via a Linear Elastic Model. This project is conducted in collaboration with Dr. Michael Dmitriev here at Texas A&M, and I'm extremely grateful for his support and mentorship. Let me begin by first describing some necessary background. The first thing to know is that this project has to do with a special material called a polymer gel. There are three components involved in a polymer gel: polymers, crosslinks, and solvent. Polymer strands are made up of chemically bonded monomers, and crosslinks are essentially bonds between the strands, as you can see in the image showing some cross-linked polymers in the middle of the screen. When some type of solvent, such as water, is added to the polymer and crosslinks, it swells the gel. You can think of a polymer gel as a substance similar to Jell-O, which can take on the shape of its container. An interesting characteristic of polymer gels is that they can swell or deswell in the presence of solvent. For example, hydrogels, which include polymers and water, can swell as in the image shown on the top right, where the gel is 95% water. Or they can deswell as in the bottom right image, where the gel is only approximately 5% water. In the swollen state, the volume of the gel can expand up to 1 to 2 orders of magnitude larger than its deswollen state. Some gels exhibit a discontinuous phase transition between their swollen and deswollen states, such that there exists parts of the material in the swollen phase, while other parts of the material are in the deswollen phase. This case is our primary focus for this research. So, the objective of this project is to simulate the equilibrium state of a polymer gel under various inhomogeneous conditions, since we want to answer the question, how does gel shape depend on the arrangement of swollen and deswollen domains within the gel and vice versa? Before describing our procedure, let me explain why we have chosen the method that follows. These types of problems, called poroelastic problems, are complex to model. And while there are programs out there that can solve problems of this nature, they're expensive. Our chosen software, Morpho, is an open source software that is designed for geometric optimization problems. Morpho was created by Professor Timothy Atherton's group at Tufts. Given a field and a domain over which the field is defined, Morpho calculates a solution that minimizes the energy, while optimizing the shape of the domain. This approach is less computationally expensive and generates rapid approximate solutions through repeated iterations of the optimization package. In our model, we keep track of the initial or reference domain as well as the deformed domain. The deformations between the two configurations are described by the strain tensor epsilon and include an energetic penalty given by the elastic energy piece integrated over the reference domain. Then, a solvent concentration field is introduced over the deformed domain with a special term for the swelling pressure. Morpho works by simultaneously optimizing the shape and field to give us these concentration profiles. So here we use a slightly different form of the same equation given on the previous slide. There are several important features in this equation to note. First, Y is the Young's modulus, which is a property of the material that describes how stiff the material is in terms of elasticity, and is a proportionality constant that relates stress and strain. J is essentially a phase stiffness, which determines the sharpness of the interface between the swollen and deswollen phases by introducing a spatial variation cost within the solvent concentration. K, or kappa, is the curvature variable, which controls the height of the energy barrier between the energy basins, which are negative C1 and C1 in the graph below. Finally, P naught is a swelling pressure, which limits the extent to which the local solvent concentration is able to expand and compress within the gel. by imposing specific boundary conditions and varying the Young's modulus between three values of 0.1, 1, and 10, we can get an idea of the concentration profiles under certain conditions. Without a swelling pressure, we have the same energy cost for both of the energy basins, negative C1 and C1, so our curve will be symmetric, as shown in the plot below. When we have some non-zero swelling pressure, our curve will not be symmetric anymore, but will instead have one energy basin that is higher than the other, as shown below. Here, our swelling pressure specifically is P0 equal to 0.25. Other than this, our method of imposing boundary conditions and simultaneously optimizing the shape and field configurations of the domain function the same way as previously without the swelling pressure, while we once again vary the Young's modulus between the values of 0.1, 1, and 10. In this slide, we can see some of the results when there is no swelling pressure, or P0 equals 0. On the right, visuals of a square domain are shown after the shape and field optimization performed by Morpho. The light colors indicate a higher concentration of water, aka a swollen phase, while the dark colors indicate a lower concentration of water, or a deswollen phase. You can see the differences in the images to the right between when the Young's modulus is set as 0.1, 1, and 10. The light and dark regions have lower energy densities than when C equals 0 in the middle, and so the optimal condition is for these areas to be occupied, aka maximized, while the middle portion, where there is a higher energy density, is minimized. On the left is a plot displaying the concentration profiles of these conditions, with the black dotted line being the expected curve for a concentration profile without swelling pressure. This concentration curve is the TAMU profile expected for an infinitely wide, completely rigid material. All of these curves are symmetric, which makes sense based on the energetic costs of the negative C1 and C1 energy basins, as noted previously, and as shown in the images to the right. So our model appears to be reliable. When a swelling pressure is added, notice the changes in the domains as shown in the right. Here the swelling pressure is equal to P0 equal to 0.25. Again, with the added pressure of the swelling conditions, the concentration profiles shown in the graph to the left are no longer symmetric, which is what would be expected. Notice also that in the profiles given to the right, we have a larger occupied area on the right of the visual, where the light color or the swollen phase is, whereas the dark color on the left is slightly smaller, which indicates the deswollen phase, particularly when the Young's modulus is set to 10. Finally, this research can be extended to more complex domains, such as a superellipse, which involves geometric curvature. These concentration profiles occur from a trace taken from the inside of the material to the outside, since it would be symmetric on both sides of the middle cut. This process is the same as the previous two Morpho iterations, but with a superellipse domain, and slightly different boundary conditions for the inner circle as compared to the outside of the shape. To conclude, we have simulated the equilibrium state of a gel under various inhomogeneous conditions by using a model that incorporates elastic and concentration energy costs. Our code, implemented in the open source Morpho software, aims to minimize those energetic costs while maximizing shape elasticity over different deformed domains. These produce concentration profiles that align with what we would expect. Our future work includes verifying this model with the existing Flory-Renner gel model, investigating buckling instabilities with phase separation, establishing a pipeline for prototyping target deformations and mechanical responses, templating inhomogeneous regions of rigidity, and building additional elasticity functionality into Morpho. Thank you so much for listening.